This week, we'll be looking at the criteria for establishing a cause-effect relationship. We'll also be discussing the role of experimental control in designing research studies, and also being able to describe the general categories of threats to internal and external validity. Experimental research asks the why question. Experimental research is also referred to as mechanistic research just because the general goal is to discover the underlying mechanisms or processes that explain how something works. So when we kind of look at descriptive research studies, this is where they have provided some sort of relationship between two variables, while the experimental research or the studies look at the exact mechanisms. So for example, we can look at smoking and lung cancer, where the descriptive research kind of looks at smoking and lung cancer, while the experimental studies take that a little bit step further and then look at the mechanisms which smoking causes actual lung cancer. So in general, the purpose of these experimental research studies is looking at and exploring the cause-effect relationship, which is defined as the association between two variables in which one variable precedes and leads to the other in a predictable fashion. So remember, in Chapter 1, we looked at two different variables, the independent variable and the dependent variable. When we look at the independent variable, this is often referred to as the cause in a cause-effect relationship. Another way that we can think about the independent variable is that it's the variable of interest, or what is driving the reason for the study or research study that you are conducting. The independent variable is also what the researchers want to manipulate in a research study. So let's say we, for an example, we conduct a study on aerobic training at 60% VO2 max, but at two different time lengths, such as 30 minutes and 60 minutes. And we want to look at, body composition, blood pressure, and heart rate before and after 12 weeks of training. And also, to help strengthen our research design, we can add a control group. So, when we look at, the 30 minutes and 60 minutes, when we place individuals in those groups are known as experimental groups, while, individuals who aren't exercising are referred to as the control group. We can also look at, other things as well when we're talking about the independent variable. Since the thing that we're manipulating is the time on aerobic training, and that would be 30 minutes and 60 minutes, but we also can refer to looking the dosage or the amount of time or so forth, depending on what type of study you're doing, and that is going to be the experimental treatment. So the experimental treatment for this example would be kind of two different ways. The experimental treatment would be 30 minutes and then also 60 minutes. So you can see with the experimental treatment, it can go different ways. If we were taking some sort of drug or some sort of supplement, we would give some sort of exact dosage for the experimental group, and so forth. For the dependent variable, this is referred to as the effect in a cause-effect relationship. So the dependent variable are the things that are being measured that are expected to change in some sort of way due to the influence of the independent variable. So kind of going back to our example of our VO2 max study and looking at body composition, blood pressure, and heart rate, and the two different experimental treatments of 30 and 60 minutes, our dependent variables are going to be body composition, blood pressure, and heart rate, while the independent variables are going to be, the 30 minutes and 60 minutes as far as aerobic training goes. So we want to, see, does 30 minutes or 60 minutes have, a greater effect on these different variables. So for cause-effect relationships, there are many examples where there's a relationship between two factors, but no actual cause-effect relationship. So we can give you an example, say, by looking at the relationship between weight and running speed, or height and reading ability among elementary children. So we most likely will find a strong positive correlation between those two variables. However, when we actually look at the relationship, there is actually no cause-effect relationship, just because height and weight in children will increase as a function of growth. So running speed will increase just because of maturation of the neuromuscular system, and then reading ability will increase just by reading continuously and through instruction. So there is actually no cause-effect relationship when you think of that. So how does one exist then? This cause-effect must meet certain criteria to actually be true. And when we think of this, or the criteria list, is that one, there's a strong correlation between the cause and the effect. The cause precedes the effect. Another criteria that needs to be met is that the cause always produces the effect, in which, in this case, in the absence of some other simultaneously acting factor intervening. And then the last criteria is there is not a viable alternative explanation for the effect. So the cause-effect relationships can only be shown through some well-controlled experiments with sound logical interpretation of the results. So there are a number of things that the researcher should take into account in order for the results to be meaningful. So, one thing that's very important during research studies is ensuring that the testing conditions are exactly the same for all participants. So this is a big consideration just because we want to kind of eliminate extraneous variables. So these extraneous variables are factors other than the independent variables that can exert an effect on the measures of the dependent variables. In a sense, these variables are not part of the study, right? Whenever you are kind of thinking of your research study. So just for example, if you were doing some sort of resistance training study and comparing, different repetitions and schemes, on muscle growth and strength, you wouldn't want individuals taking creatine for that. So just because, if you have individuals taking creatine, that might influence the results for one group or some sort of repetition scheme that you're looking at. So by doing so, we want to have some sort of experimental control, and by doing that, we have the ability to eliminate all influences other than the independent variable that can affect the dependent variable. So this is just assuring that the data isn't contaminated, say again, by taking creatine. So we have a kind of more meaningful interpretation of the results and can, make a solid recommendation on what repetition scheme is best for muscle growth and strength. Another example of how we can provide some sort of experimental control besides not having individuals take some sort of supplement such as creatine, and the last example is that we can provide a control group. So let's say, for example, we want to look at sleep deprivation, where we'll have group 1 be sleep deprived and group 2 being a non-sleep deprived group. So, the goal of a control group is that the participants are measured for the dependent variables, but they do not receive any experimental treatment. So in this case, or this example, group 2 is the non-sleep deprived group, and that is going to be our control group. So a control group provides a set of comparison data that will help to more definitively show the effects of the experiment, such as the dosage or some sort of time frame on what you're really looking at. So the inclusion of a control group is very invaluable in an experimental research study and can help strengthen your research design and make a little bit more sense on your results. In some cases, there may be some variables that exist that can potentially affect the outcome of the study, but for various reasons in which the researchers cannot eliminate them. So, for example, whenever you are recruiting participants, they may be, very experienced at taking some sort of test of the dependent variable that you're trying to measure, which would, lead to some sort of improvement in their performances. But most likely, and obviously, you're not going to know as the researcher that they have this, experience. And in this case, in these factors, where they may influence the results but cannot be eliminated, this is referred to as your confounding variable, and this is uncontrolled factors other than the independent variables that influence the measures of the dependent variables. So good research studies produce results that accurately reflect the effects of the independent variables on the dependent variables on the participants that you are studying. And when these two conditions are met, the results of the study can be said to have some strong validity. So validity is the ability of a research study to faithfully reflect the true state of the variables being studied in the population of interest. So when we think of validity, this can be broken into two different categories: internal validity and external validity. Internal validity is the ability to conclude that only the independent variables affected any differences in measures of the dependent variables across groups or across tests on the same group. So to consider to have good internal validity, the researchers attempt to control all extraneous factors that might affect the dependent variables. So there is, a possibility that the dependent variables can have been affected by a factor other than the independent variable for your research study. And this is a plausible rival hypothesis. And this is where a proposal that something other than the independent variable affected measures of the dependent variables. And for this, we need to try and eliminate. So just to give you an example, a plausible rival hypothesis might be that, the participants in one group didn't perform exercises correctly because the exercises were too complicated or not well explained whenever you are, going over them during the research process. And by doing so, this is going to, negate, the ability to compare the effects of the two protocols. Another one may be, lack of motivation. For some participants, there can be some other various reasons, but a well-designed study, the researchers, carefully plan such that any changes in the dependent variables can only be attributed to the treatment dosage of the independent variable, and there are, no plausible rival hypotheses. The second important consideration when designing research studies is external validity. So external validity is the ability to generalize the results of a study to the sample population in the real-world setting. So the consideration is always the extent to which the participants represent the general population. And with this, the population is the large group to which the results of a study conducted on a sample of that group may be generalized. So with this, we can actually have, some sort of definition or kind of define a population of interest, such as young, healthy men and women, elderly, even resistance training whenever we are, looking at our research study or trying to conduct a research study. But we refer to the group of the participants selected as being representative of that given population as the sample. So the participants involved in a research study are considered to be a representation sample of the larger population. The only thing, though, is that we can only generalize the findings to that defined population that you set. So if we did a study on young, healthy men and women and found the results, we cannot apply it to the elderly, just only that defined population. Good external validity is based in part on making sure that the study participants are accurately representative of the population to which you want to be able to generalize results. So this is the importance of having inclusion criteria and exclusion criteria for your research study. So inclusion criteria is the list of characteristics that individuals must possess in order to qualify as participants in a study. So for example, you can have an inclusion criteria of age range, gender, training status, etc. This will be based on your research question. For the exclusion criteria, this is the list of characteristics that individuals cannot possess in order to qualify as participants in the study. And again, some examples that you can utilize is having recent injury, if they're a tobacco smoker or obese. And again, this is all going to be based off your research question. By having this criteria, we can narrowly define a population depending on the length of the list that you have. So one way we can as researchers have confidence that the sample size is truly representative of the population is to randomly select participants from the population. Ecological validity is the other major component of external validity. So ecological validity is the extent to which the testing conditions in a study are like the conditions in the environment being studied. In this case, it is closely mimicking real-world conditions. So for example, if you want to test out a new energy drink on marathon running, you can look at the variables in the laboratory setting or the field setting. So when you're looking at the performance in a laboratory setting, the runners may not perform or behave as if they were actually outside running. So this could be considered of having poor external validity. But if you look at the performance outside in which they are used to running, then the results could be more meaningful for your research study. So just know that there are going to be advantages and disadvantages when testing in a laboratory setting and field setting. When planning a study, researchers must make decisions regarding the study design with sensitivity to the implications for internal and external validity. So no study design can optimize both. So therefore, smart decision making in designing a study relies in part on understanding the factors that can threaten the integrity of internal and external validity. So one threat to internal validity is history, where something other than the experimental treatment can affect the dependent variable over a period of time. So for example, if the treatment involves an exercise protocol and some of the participants are getting additional exercise through participation in an organized sport, this can influence the results. So a way to avoid this threat is to include sport participation in the exclusion criteria list. Another threat is maturation, which refers to things naturally occurring over a time period that can influence data such as aging. So this can be an issue when performing a study on children. So if your study is long enough, the children will become bigger and stronger and then also develop better skills, which can again influence the results for your study. Another threat is testing, which is another threat to a study that involves one or more repetitions of the same test just because of the potential practice effect. So taking the test the first time serves as the practice on that test, and then subsequent tests will have better performance. Instrumentation refers to the potential sources of data error resulting from the data collection process, such as equipment malfunction, software bugs, or misusing a piece of equipment. So when a study involves the use of observers, there's the potential for recorded observations to vary over time and across conditions, which can also be a threat to internal validity. Statistical regression becomes a possibility when groups are formed based on extreme scores. So if you have one group perform a test really well at the beginning of a study and place them together, and another group perform poorly or have low scores on a test and place them in a group by the end of the study, it will show that the highest score group scores get lower and the lowest score group gets higher. Another threat to internal validity is selection bias, which is the comparison of groups that are not equal at the beginning of the study. So we want the groups to be, similar so that the treatment is valid when we are comparing two or more groups. So by placing participants randomly, we can assume that the groups will likely be similar. So therefore, the best way to control for selection bias is random assignment of participants to a group. Experimental mortality refers to participants withdrawing from a study for any reason. If there are just a few participants that drop out or withdraw, then the threat is minor, but if there's a big dropout, then it can cause an issue when trying to compare groups. One thing to consider is that you may need to avoid performing a study during the flu season where a participant may be out for a while and miss more treatments than necessary. Also, you may need to halt a training protocol if the participants are becoming injured from it, and this is a result from a poor design study. Another threat to internal validity is selection, maturation, interaction, which is a threat where maturation affects groups within the study differently. So let's say, for example, you want to look at a certain age range of young individuals and a certain age range for the elderly. If you have a study that exceeds over a length of time, there is that potential effect that the aging process may affect the elderly group differently compared to the younger group. So the last threat to internal validity is expectancy, and such that the researchers tend to expect one set of scores to be better than another. So again, an example for this threat is that you may expect that post-test scores be better than pre-test scores, or one group will perform better than the other. So the effect is the same thing whether the person who measures or rates the outcome variable is conscious or unconscious of the expectancy. So expectancy can become a threat if measures are not taken to ensure objectivity in the assessment and recording of the data. So using multiple raters or going through rater training may help minimize this threat. When we look at the threats to external validity, one is the interaction effect of testing. This is a potential threat for studies involving a pretest prior to an experimental treatment. So if you give a pretest and provide the participant their score and they think that they were performing poorly or have a low score, they could use that value and turn it into some sort of motivation for the treatment and affect the results. So to minimize this threat, it is best not to share their values until they are completely done with the study. Another threat to external validity is the interaction of selection bias and experimental treatment, which is a threat where a biased sample produces skewed results not representative of the population. Say you want to survey the athletes on campus on their dietary intake, but 60% of the surveys that are submitted is from football players. The results do not represent any other population or athlete population besides the football players. So this threat becomes an issue when the sample is biased and or the population to which the results are generalized is defined too broadly. A reactive effects of experiment setting is an external validity threat whenever the setting in which data are collected cause the participants to behave differently than they normally would, such as a laboratory setting versus a field or a competitive setting. There is a specific type of reactive effect known as the Hawthorne effect, which is a phenomenon in which participants' performances during a research study improve due solely to the fact that they know they are being observed. The last threat to external validity is the multiple treatment interference effect, where experiencing one treatment affects participant response to a subsequent treatment. So this response can be either positive or negative. So for example, students usually perform better on the second exam compared to the first exam just because the first exam alerted them to the kinds of questions the professor is likely to ask and also the type of style of questions. Alternatively, if students think the first exam was easy, then they might not study as well for the second exam. So this effect can become an issue in research studies that test more than one experimental treatment on the same participants. When designing a study, researchers make decisions about things such as how many groups are needed, the number of participants, what experimental treatments will be given, and then how many times data will be collected, which is often referred to as repeated measures. So these decisions are based on the nature of the research question, controlling as many threats to internal and external validity as possible, which we just mentioned, and then also some practical considerations such as the time invested and the cost of data collection, such as can you travel to certain events if you need to collect some data, some equipment costs such as ultrasound gel if you're trying to look at muscle thickness, but those are some things that you need to consider. If you want to optimize internal validity, that will be more related to having a highly controlled laboratory environment, while optimizing external validity will be related to collecting data in a field setting, which is less control compared to the laboratory setting, but provides more of a real-world setting. There are some common research designs that can be placed into three categories: pre-experimental designs, true experimental designs, and quasi-experimental designs. The pre-experimental designs are weak designs that do not utilize random assignment of participants to groups and control very few threats to validity. So these types of designs doesn't allow for a conclusive determination of cause-effect relationships. Also, these designs are usually selected due to practical constraints, and one thing to note is that these designs are to be avoided. When looking at pre-experimental designs, it may consist of a one-shot study, which involves one group of participants that receives a treatment, and this is designated as T, followed by data collection, where this is designated as D, to assess the effects of the treatment. So of this study design, nothing can be concluded from this type of study because you cannot determine whether the treatment had any effect on the participants. So let's just take, for example, if one class were to only give one exam, which would be the data collection portion at the end of the semester. And based on the results of that exam, you can draw conclusions about the quality of instruction in the course. In this case, the course would be the treatment. So this is kind of an example of a one-shot study. So this is a design that is clearly very poor in a way to attempt to help answer a research question, and it should be somewhat avoided. The next design is the one-group pre-test, post-test. So this is an improvement on the one-shot study in that the post-test data can be compared to the pre-test data to determine whether a change occurred. A downside of this design is that you cannot conclude that any change reflected in the post-test data is based upon the treatment. So history, maturation, and testing effects all threaten the internal validity. The static group comparison design offers an advantage and a weakness compared to the one-group pre-test, post-test design. So the advantage is that there's a second group, which is the control group, and the control group does not receive the treatment, so the results of the two groups can be compared. A weakness of this design is that there is no pretest, so we cannot assure that the groups were equal at the beginning of the research study. So in this design, selection bias and selection maturation interaction are threats to the validity. It is sometimes, though, used of necessity when circumstances do not readily allow random assignment of participants. True experimental designs are designs that begin with random assignment of participants to groups, thereby controlling most threats to internal validity. So by requiring these random assignment of participants to groups in these designs, it helps control for internal validity threats such as the history, maturation, testing, statistical regression, selection bias, and selection maturation interaction. The post-test only design is the same as the static group comparison design, but with the exception of random assignments of groups, which is indicated by the letter R on the slide. So since the design randomized participants to groups, the researchers can have a good measure of confidence that the groups are similar for measures of the dependent variables at the start of the study. Also, the presence of a control group enables conclusions that any changes in the dependent variables for the experimental group are due to the effect of the treatment and not to extraneous variables. The pretest post-test design builds upon the post-test only design by adding a pretest. So this addition of the pretest gives the researchers the ability to conclusively demonstrate that the groups were equivalent at the start of the study for the variables being measured. The Solomon 4-group design is a sophisticated design that will always include 4 groups. So the purpose of this design is to test the effects of the experimental treatment, but also for any reactive effects. So we can also determine whether the treatment or the pretest had a greater effect on the participants. So this design is used where there is a real concern that the pretest will exert a powerful influence on post-testing measurements, which is a concern with tests of skill. A disadvantage, though, is that a large number of participants must be involved since we are having 4 groups. Quasi-experimental designs are specialized for optimizing external validity, which again is collecting data in a field setting where there is less control but more of a real-world setting. So the quasi-experimental designs are used when circumstances prevent random assignment of participants to groups. A time series design involves repeated measurements of the same dependent variable or variables taken on one group of participants over a certain time interval. For the research to be experimental and not descriptive, there must be a treatment at some point among the observations. So with this design is used when researchers expect there to be incremental changes occurring over time, which may be due to maturation or testing effects. Probably the most common way to implement a time series design is in case studies of single participants where repeated measures are recorded at regular time intervals. Equivalent time sample design provides a variation on the time series design where this design involves at least 2 applications of the experimental treatment among the periodic data collections. So this looks at testing not only the effects of the treatment, but also to what extent there is a lasting effect of the treatment. This type of design is often used in studies of the efficacy of a new drug. Non-equivalent control group design is like the pre-test, post-test design, but without the random assignment of participants to groups. So the reason why some researchers may choose this type of design is that in some circumstances, random assignment to groups is either inconvenient or simply not possible. The last quasi-experimental design is the ex post facto design. This is based not on the experimental arrangement, but on the nature of the groups being compared. So when treatment is not controlled by the researchers, the design is ex post facto. So an example of this is in studies measuring one or more dependent variables to compare men and women, and where the treatment is gender. Things that need to be completed by Monday, October 19th by 11:59 p.m. is taking quiz 6, then also the article review assignment by Dankel and colleagues.